Okay, vector quantities have magnitude and direction, so adding them is more like geometry than you would think physics. So there's a couple ways you can actually physically uh, do the addition. I say physically, I mean draw it out on a piece of graph paper. So that's what I'm going to do with this. You have to get a rough idea of where we're going so you don't end up off the page. But first we're going 40 at west of south, so that's like uh, this direction. So we're going to go like 40, and then we're going to go 60 north of west, so that's going to be like this way. We're going to go 60, and then we're going to go east of north, so it's going to be this way. So I'm going to start over here. I'm going to set my home right there, and we're going 90. That's the biggest one, so I'm going to try to set a scale of let's see, 40 would only be this long, 60 this long, 90, that might do. So if this is my start position, I'm going to add these vectors graphically, or in other words, what I call head to tail. I'm going to line this up, and let's see, I'm going to make sure you can actually see what I'm doing. I need 36.9 degrees west of south. Well, this direction's south, so 10, 20, 30, 6.9. So see, no, this is going to be a little rougher than an actual calculation because you can see that I can't estimate 36.9 very well. In fact, I don't even think I hit it. 10, 20, 30, 5, 6. I need a finer point, don't I? It's like right in there. There. Okay, so and I'm going to go 40 that direction. So my ruler's a little messed up on the end, so I'm going to use 1 centimeter is 10. So 10, 20, 30, 40. So that puts us right there. So that's my first vector. Now from here, I'm going to go north of west. So this is going to take just a little bit of guessing to make sure that I'm parallel with those lines, as you can see. And I'm going to go 56 north of west. This way's west. So north of west would be 10, 20, 30, 40, 50, 6.4. Right there. Ooh, I may still go off my page. Hard to tell. We'll see. So I want to go 60 in that direction. Well, I can just line it up here. So 10, 20, 30, 40, 50, 60. So there's the second one. So this is vector A. Vector B, notice head to tail. So the head of this vector, tail of this vector. And then last, I need to go 60 or 65 degrees east of north. So 65 degrees east of north. 10, and this is north and I'm going east of it. So 10, 20, 30, 40, 50, 65.5. Right there. And I want to go 90. Oh, I hope I don't run off the page. Should have started more towards the center. We'll see what happens here. So, oh, I'm going to be close to being off the page. So we go 10, 20, 30, 40, 50, 60, 70, 80, 90. Right there. Okay, so that's my last vector. So adding those vectors will be from the beginning to the end. we just draw an arrow. You can make it a different color if you want to or whatever, but so you can keep track of it. So this is vector C. This vector here we normally call the resultant, and it's equal to A plus B plus C. Well, what is that vector? Well, like I said, this is just like a brute force method of handling. We'll just measure it. And let's see, from where we started to where we end, 10, 20, 30, 40, 50, looks like 61 maybe. This is going to be rough. This is 61 meters per second. And the angle, it's going to be even harder to see. We line this back up, and it looks like, I bet I turn this over, it might be easier to read without having to count them. Lined up good. Looks like about 66 degrees, so north of east. So when we add these three vectors, we should, when we add them analytically, we should get about 61 meters per second at 66 degrees north of east, provided I did all this right. So let's see how that turns out. We're going to now add these analytically. To do that, you need just a little bit of understanding of how to write vectors and their components. So in the notes section here, I'm just going to quickly jot down a vector. Let's see. I'll make a horizontal axis and vertical. I need, oops. Okay, so vertical axis. Now, I normally refer to these as X and Y, but you could say east, north, south, and west. You just need to keep track of it. Any vector that you draw like this, call it just vector A. It could be anything. It could be a velocity, acceleration, whatever, and an angle theta. Can be thought of as two vectors. I'm going to try to get this perpendicular the best I can. Can be thought of as two vectors. I usually draw these vectors as sort of shaded lines because they're not vectors, they're components of this vector, but we think of them as being like vectors along the axis. In other words, if we added two vectors along the axis together to get A, it would be these two. So we call them A sub X and A sub Y. Now you probably remember from your trig that the definition of the sine of theta is the opposite over the hypotenuse. So AY over A. Because it's a vector, we have to think of this as being the magnitude of A. Okay, so you just really should have magnitude signs around that. That means A sub Y, the Y component, is just going to be A sine theta. And likewise, the definition of cosine theta is A sub X over A. So A sub X is A cosine theta. Okay? That's how you break any vector up into its components along the X and Y axis, provided theta is specified from the X axis going in the counterclockwise direction. These two equations will always work as long as theta specified from plus X axis going counterclockwise. Okay? Now, if we knew a sub x and a sub y, or you call it r sub x and r sub y, if we know the components of a vector, then we also know the vector, because you can use the Pythagorean theorem to show that, we use the Pythagorean theorem to show that a sub x squared plus a sub y squared equals a squared, or the magnitude of a is the square root of a sub x squared plus a sub y squared. And the angle theta has a tangent of a sub y over a sub x. That's the definition of the tangent. Therefore, theta will equal the inverse tangent, or some books call arctangent, of a sub y over a sub x. Okay, so these two equations will help you reconstitute a vector if you know its components, any vector. Okay, so there's your notes. The book's a little more thorough. This is really brief. But now I want to add these vectors by their components. All right, the only tricky thing about doing that here is what I said about specifying the vectors from the positive x-axis going in the counterclockwise direction. Notice the first one that we saw was 40 meters per second at 36.9 west of south. I need, well, I'm going to draw that out here to the side, just a rough sketch of this out here. So we have this first one is 36.9 west of south. Here's south. West of south would be going like this. So this angle right here is 36.9. This is 40 meters per second. So this angle would be 270 minus 36.9. Or 233.1. So the x component of A would be 40 meters per second cosine 233.1. Okay, the second vector, just a rough sketch of it, is 56.4 degrees north of west. Here's west. North of west is this way. So up here, this angle 56.4, and this is 60. And I said it's rough. They're not even to scale. So this angle here would be 180 minus 56.4. 123.6 degrees. So the x component of B then is 60 meters per second cosine 123.6. Now for vector C, rough sketch. East of north. Here's north. East of north is this way. And this is 65.5 degrees and 90. So this angle is 90 minus 65.5. I shouldn't have to use a calculator to do that, but I'm not thinking very well today. So 24.5. So we have 90 times the cosine of 24.5. Now, we can go ahead and write these components. 40 sine 233, 60 sine 123.6, and 90 sine of 24.5. Let's just punch those. Well, technically we don't have to punch each one into the calculator. We can just add them up, which is what I'm going to let you do. I'm just going to add them up. I'm going to do 40 cosine 233.1 plus 60 cosine 123.6 plus 90 cosine 24.5, and I get 24 point, I'm going to keep an extra digit, 68. And then the y component I'm going to do the same way. 40 sine 233.1 plus 60 sine 123.6 plus 90 sine 24.5. And I get an error. What did I do wrong? Yep. Oh, let's see, maybe too many. (40 sine 233.1 plus parentheses 60 sine of 123.6 plus 90 sine 24.5. I left out a parentheses, didn't I? That's going to be 55.31. I hope I didn't mess up either one of those. I did that really fast. You can write them in a table like I did down here, like I have made available to you down here, to write each of those components as you calculate them and then add them straight down. I'm not going to take the time to do that. I am going to use the Pythagorean theorem real quick to find the magnitude, which is the square root of 24.68 squared plus 55.31 squared. Units of all these, meters per second. If I square the units and take the square root, just be meters per second. So second square root, 24.6 squared plus 55.31 squared gets me 60.6 meters per second, which is really close to what we had on the front, I think, which was 61 degrees, maybe. Let's see. 61 meters per second is what I had on the front, which is not bad for a drawing. Now the resultant, the angle, inverse tangent of 55.31 over 24.68, and the units meters per second over meters per second just cancel. They have to. You can't have an argument in your trig functions. But I'm sorry. You can't have units in the argument of a trig function. The argument being what's inside the parentheses. If you've never used the inverse trig functions, it works like this. You just hit second tan, and then you put in. You could calculate the number first and then put it in, but it'll let you put the calculation inside the argument. And we get 65.95 or 66 degrees. And let's see, my drawing, I had 66 degrees. So that's not bad for a rough sketch. So that's how you break components down. That's how you add vectors by components, and you add them graphical. I'm going to let y'all work these three and then a couple out of the book, and I'll see y'all on Monday.